In the last class, we completed the CPM, critical path analysis. For the given project, we are drawing the network, and from there we are finding what is the critical path and what are the critical activities. If you note one thing, for the critical path CPM, what we were using the time as the fixed one or the deterministic one. Now, if the time of the activity of the time, if it is not deterministic, if it follows some probability distribution, in that case what to do? For that, today we will start the next one, that is the part, that is program evaluation review technique. If you see this program evaluation review technique, this was developed by US Navy for Polaris missile project. For this project it was developed, and it can handle the uncertain uncertain activity time. Basically, if you see, the part uses the three concepts, three cases: the most optimistic, the most pessimistic, and most likely duration. Please note this one: most optimistic, most pessimistic, and most likely duration. It determines the probability for each duration, whereas CPM considers most likely duration. I will talk about these points one after another. Let me just tell you the advantages of CPM, or where we should use the CPM. It is useful for very large projects, straightforward concept, and mathematically it is simple, that is mathematically it is easy to implement. Graphical network help us to understand the relationship among the project activities, that is the nodes are there, and among the nodes what are the different relationships, what are the critical activities, that thing we were finding out easily through CPM. And the last point is critical path pinpoints the activities that need to be closely watched. That is, what are the critical activities, and these critical activities has to be completed in time, otherwise your project duration time will also be delayed. So, from this critical path analysis we can get what are the critical path, what are the critical activities, and we should monitor more on which activities. In CPM we use basically, if you see, the single estimate of time. In the problems you are seeing that to complete a particular activity, what is the time? That is the estimated time, single estimated time. But in part, basically if you see, there are three time estimates which we will use. One we call it as the optimistic time, another one is the most likely time, and the pessimistic time. Let us see what is optimistic time. The optimistic time we will talk in notation, we will use it at T0. Time estimate of an activity when everything is assumed to go well as per plan. In this, it is the estimate of the minimum possible time which an activity takes for completion under ideal condition. That is, if everything goes on smoothly, then what is the time taken, that we call as the optimistic time. Whereas, most likely time is the time which the activity will take most frequently if performed a number of times. That is, we call it as the mode value. That is, if the same operation we are performing a number of times, then the most frequently whatever time it takes to complete one activity, that we call as the most likely time, and we denote it as Tm. As you see, we denote it by Tm, and this is basically nothing but the mode value. In terms of probability, we can tell it is the mode value. The last one is the pessimistic time. This is unlikely, but the time estimate when everything is assumed opposite to the plan. If you see everything assumed opposite to the plan, then the longest time the activity can take in worst case. That is, we are assuming that nothing will go as per our plan. In the worst case, whatever time it takes, that we call as the pessimistic time. Of course, this time excludes the major catastrophics like labor strike or the act of God, like this. So, from this, if you see, these three time estimates are combined statistically to give the expected time for an activity. So, basically we will use these three type of times, the most likely, most optimistic time, most likely time, and the pessimistic time, and using this three times together statistically we will try to find out what is the expected time for an activity or expected completion time. So, what is the fundamental assumption of PERT is that these three time estimates from the endpoints and mode of beta distribution. I am not going to the beta distribution. What is beta distribution? Because that will take much more time. So, for the beta distribution, if you consider these 3 points, basically these 3 times 2 gives the endpoints and another one gives the mode of this. Then we have to basically from these 3 times we have to find out the expected time. Expected time, which we will denote by T e. This divides the area under the density curve. If you draw a density curve, then whatever way you draw it, the density curve something like this way, you can say this is the middle portion. So, if you see, it is dividing basically into the expected time is dividing into 2 parts. This T time denotes in which there is 50-50 chance of an activity being completed. That is T e, we are the expected time whatever you are calculating, that is the time that there is a chance of 50% that the project will be completed in time or project will be failed in time. So, you are having the 3 times T 0, T p and T m. From this T 0, T p and T m, using these 3 times you are calculating the estimated time, and using the estimated time then we will further analysis our project. The next step is the basic reason to estimate more than one time for an activity is to provide data by which management may determine the probabilities that each activity as well as the entire project will be completed by a deadline. That means, we want to say here is that whenever you are repeating a particular experiment, it is something like that you are repeating the experiment. Whenever I am repeating the experiment, in that case we are getting different kind of results, and from there you are finding out the most expected time for the completion of the project. That is the reason we go for the repetition. Then several formulas are used for this purpose along with the normal probability table. We have the tables. We will not go into details of this one. Range determined by the optimistic time T 0 and the pessimistic time T p must enclose every possible estimate of the duration of the activity. That is, optimistic time and pessimistic time should tell you the endpoints of your project duration. That is, what should be the minimum time it should take and what should be the maximum time it should take, that should be estimated properly. The next step is the most likely time T m. It usually may not be same as the midpoint of T 0 and T p, that is T 0 and T p plus by 2. It may not be the middle point, please note this one, most likely time. It may be slightly deviations from the middle point T 0 plus T p by 2. And keeping this thing in mind, the above mentioned facts, it may be justified to assume that the duration of each activity may follow the beta distribution with its unimodal point occurring at T m and the endpoints at T 0 and T p. So, basically if you see, there are T 0 will be here, T p will be here and the unimodal point T m somewhere it will be here. So, for a beta distribution we are assuming that the endpoints will be T 0 and T p and the unimodal point this will be T m. So, in the beta distribution is T m is weighted half as T 0 plus T p by 2. Thus, the expected value, that is T e. T e can be obtained using this formula. T e is equals to twice T m plus T 0 plus T p by 2, T 0 plus T p by 2, that is the midpoint plus twice into this the unimodal point. And if you calculate this, this will be T 0 plus 4 T m plus T p divided by 6. So, your expected time T e, if you see, this is T 0 plus 4 T m plus T p by c. So, what is happening for a particular project? Basically, whenever you are for a project you are calculating the T 0, you are calculating the T p, and from there you are calculating what should be the most likely time. Once I know these 3 values T 0, T m and T p, using this formula T e equals T 0 plus 4 T m plus 4 T m plus T p by 6, using this formula you can calculate the expected time, that is TE. Since the almost, that is, it is statistically it has been observed 99.06% values of a random variable fall within plus minus 3 standard deviation from the mean. Mean means assuming, of course, we are assuming the normal distribution. Then the length of the interval, that T naught and T p is almost 6 times the standard deviation. That is T p minus T naught, if you see T p minus T naught, this is equals to, we can say that 6 sigma, that is sigma is the standard deviation. So, from here you can tell that sigma is nothing but the T p minus T naught divided by 6, and from here you can calculate the sigma square also, T p minus T naught whole square by 36. So, what we want to say from here is that once I know T p and T naught, from here what should be the standard deviation, that also I can calculate the 6 times of the standard deviation. From there I am telling T p minus T naught will be equals to 6 sigma, and from there standard deviation you can calculate. Now, negative float in a PERT network. What is negative float? You have find out the expected value, right? The expected value is your TE. Now, the value for which the schedule completion time, that we call as the expected schedule time, that we denote it as TS. So, this value TS, that is schedule completion of the project. This TS, what is the relation then between TS and TE? Your TS is your schedule completion time, whereas TE is the expected completion time. So, when TS is greater than TE, that means schedule completion time is greater than the expected completion time. So, therefore, you are having a positive float, that is you are completing it before expectation, whereas when TS is less than TE, that means you are completing the schedule after the expected time, then a negative float occurs, whereas whenever TS is equals to TE, we say that that is a 0 float. So, what is happening here? In such cases, critical activities are not specified by the condition of 0 float along the path. The critical path is the path of least float, for which such kind of PERT network in which backward pass is based on the schedule data. A negative float implies that activity must be reduced by that amount of float to keep the schedule date unchanged. Negative float means, I want to say, here you have the activity. One activity I am considering the completion time, whatever it may be, say it is 10 days. To complete this one, it may take 3 days. So, negative float means basically what I want to say, I can reduce this one, so that it should be complete within the expected time. So, I have to, the activity can be reduced further by what purpose, by how many, that we can decide, and a negative float basically arises in PERT, particularly when the mean expected project time of final event is less than the scheduled date. That is expected project time, as I was showing you, TS is less than equals less than TE. So, what should be your PERT algorithm now? Step 1, I will just tell it in briefly. For each activity, obtain the estimates of the optimistic time, pessimistic time and most likely time. As I told you, we have to calculate we have to obtain the estimates of these 3 time, T0, Tp and Tm. These 3 estimates are supplied by the project manager or someone who is familiar with these similar projects. That is, I have to estimate this. Step 2, using these estimates, compute the mean and variance of each activity by the formula. That is, you are calculating the variance, you are calculating the expected time Te using the formula just before 1-2 slides we told. Step number 3, based on mean activity time, determine the critical path by CPM. Now, you are using the mean activity time, then you are calculating the critical paths by CPM, the method which already we have done. Once number 4, once the activities are identified as the critical activities, then add the mean and variance of the critical activities to find the mean and variance of the project completion time. That is, once you have identified the critical activities, then I have to find out the means. We have to use the mean and variances of the critical activities, and we can find the mean and variance of the project completion time. Total project completion time is normally distributed with the mean and variance determined in step 4. This part, if you see, we will discuss this one again once we are going through the problems. Now, time cost trade off in PERT. The project manager sometimes may have the option of crashing the activity, spending extra money to compress an activity's duration by which overtime, by using the overtime, subcontracting, expediting materials, etc. Now, what do you mean by crash? That you have to understand. What do you mean by this crash? What do we want to say here? From one activity to another activity, suppose it takes 7 days, and the crash time, that is, if I enforce, as I was telling you, if we enforce the extra labor or if we give overtime, I can complete this by 5 days, say. This activity I can complete it by 5 days if I give overtime or if I include some more extra manpower. That means, I am ready to make more expenditure, but by that means I am reducing the time of the completion of one activity. And once you are completing, you are compressing the activity, that means schedule time will also be reduced. So, this concept we call it as the crashing. That is, normally one activity should be finished when, and when I can crash it, then when it can be compressed. So, basically for this activity to complete, I can compress it by 2 days, not more than 2 days. Why this crashing is required? You just see the second step. In the second step, you see if there is a danger in the project or we are running out of time, project manager can find this crashing extremely useful alternative for maintaining goodwill or urgency for the completion of the project. So, basically what you are telling here, that once there is a problem, project manager is find I am running behind schedule, I cannot complete it in time. So, there is a concept of goodwill is there for the company who are executing the project, or we have to complete the project by hook or crook. Say we are organizing some Olympic games, so we are preparing the stadium and all these things, they has to be completed in schedule time. So, in these cases, by putting the extra effort, maybe in terms of manpower, material, money, we can crash the time and the activity can be shortened by its normal time. So, for this reason, the crashing concept is very useful. The next part is the what are the crashing strategies. Whenever you want to crash, the crashing strategies should be very clear. Do not crash non-critical activities. Using CPM, you know what are the critical activities, what are the non-critical activities. We are telling do not crash the non-critical activities, this will not reduce project cost in general. If you crash a non-critical activity, that is through which the critical path is not passing, then do not crash that one. We will see through one example that if you try to crash a non-critical activity, the duration of the project will not be shortened, will not be reduced. So, next point we are telling you crash only the critical activities, that is the activities on the critical path. Crash activities with lowest crashing cost per unit time until the desired project duration is achieved. So, please again note here, crash activities with lowest crashing cost, that means whenever you are crashing, you have to pay some cost. So, the activity, the critical activity for which you have the lowest cost, you please take that one. That is, I have to calculate separately what are the crashing cost for each activity. From there, I will choose for the critical activities which is the lowest crashing cost, and I will select that particular activity for the crashing purpose. The next step is when the parallel critical path exists, each of the parallel paths must be compressed and compressing alone must be compressed. That means, we want to say here, you have a critical path something like this. Say you have a figure like this, you have a figure like this. So, you have basically this is your critical path. If you see, by double line we join the critical path. Suppose this is the critical path, on both sides we are getting the critical path. It is 7, it is 4. Suppose it is 5, it is 2. So, whenever you are having two parallel critical paths, in that case if you try to, if I want to crash this activity, its parallel activity also has to be crashed, because that means I can crash both these activities by 2, not more than 2, because lowest of these 2 is 2. So, we are saying whenever there are parallel critical paths, on both of the path you have to crash, because if you crash only on this side, then you will not achieve the minimum. This project completion time will not remain same, it will be unaltered. So, in this case what you are doing, if you are crashing on this side, you have to crash on the parallel path also by the same time. So, the next one is the minimum time minimum cost network will be the final network. If penalty cost are also present, optimal network can be found by comparing the crash cost unit crash cost with the penalty cost. Next is networks path diagram can help to identify the activities whose duration should be shortened, so that completion time of the project can be minimized in the profitable manner. That we will see when we are going through the example. The next one is the process of reducing the activity duration by putting extra effort is called the crashing of the activity. This is the new thing which we have not done in CPM. In CPM only we were finding out the critical paths and what is the project duration. Now, we are saying that in part we want to learn one more thing, is that what is the normal completion time of one activity and what is the crashing time of completion of one activity, and by that amount I can crash that activity, so that I can reduce the completion time of that particular project. The next is the crash time, which we denote as TC. You see, the crash time is TC, represents the minimum possible activity duration, and attempt to further crash would only raise the activity cost without reducing the time. That means, if you try to go on reducing or crashing, one point of time will come, your project duration is not being shortened, your cost is not minimum, that is project duration is increasing, your cost is also increasing, and in that case you have to stop and your crashing time will be the earlier one whatever we have done. Through figure, if you see here, the normal cost Cn, if you see, we are using for notation Cc, that is crash cost, Tc is the crash time, Cn is the normal cost and Tn is the normal time. From the figure we have seen what is Tc, what is Tn, what is Cc, what is Cn. The relationship between this Cc and Cn is Cc must be greater than Cn always, that is crash cost must be greater than the normal cost, it is obvious. Crash cost must be greater than the normal cost, whereas the crash time should be less than the normal time, that is Tc should be less than Tn. Always Tc, that is crash time, should be less than normal time and crash cost should be greater than the normal cost, and that we have shown over the figure. If you see the figure, your A denotes the normal time for completion of the project, whereas the point B denotes the crash time for this one. If you see the curve, the cost curve from A to B, that is not a nonlinear curve, but and it is asymptotic curve also. It is nonlinear and asymptotic, but for the sake of simplicity, we can approximately join it by a straight line, and which we denote as AB. So, basically the cost curve, if you see, the cost curve is nonlinear and it is asymptotic. You see the curve nature, but for simplicity, for to get the easier formula, we are approximating this curve by the dotted straight line AB. So, that from this straight line AB you can find out the slope. What is the slope of this line AB? You see the line AB. For this line AB, the slope will be, which we are telling as cost slope, is equals to crash cost minus normal cost by normal time minus crash time. Please note this formula. Crash cost, so cost slope will be simply crash cost minus normal cost by normal time minus crash time. So, the cost slope represents the rate of increase in the cost of performing the activity per unit decreases in time, which we call as the cost or time trade off. Please note this one. Cost slope represents the rate of increase in the cost of performing the activity, rate of increase in the cost of performing the activity per unit time decreases in time, per unit which decreases in time, which we call as cost or time trade off. Now, next is the probability of meeting the scheduled time. We have a scheduled time. Now, what is the probability that the project will be completed in scheduled time? You have drawn the figure, you have drawn the critical path activity, everything you have drawn. After that, someone wants to know what is my position now, whether I can complete it in scheduled time or not. For that one, how to calculate? For this, we are just see the formulas. With PERT, it is possible to determine the probability of project completion on schedule. The scheduled dates are expressed as a number of time units from the present time. Initially, there may be the latest time TL for each event, but your after initiation or starting of the project manager should know how far it has progressed and at any given date, and the schedule time will be the least time if the project is to be completed on its original duration. That is at the middle of the point, at the middle of the project, if I want to know what is the guarantee that the project will be completed in schedule or not. For that one, we are using this. The probability duration of completing an event is approximated by the normal distribution, and this is done by the central limit theorem. We are not going to that one. So, basically you are using this formula, probability of Z less than T s minus T e by sigma e, T s minus T e by sigma e. I am telling sigma e means expected, that I will talk. So, I want to find out this probability, basically probability of Z less than T s minus T e by sigma e. Here, if you know at a point of time in the middle of the project, I can find out what is the expected completion time, I can find out what is the sigma e, and I have to find out what? I have to find out the value of this T s. We have told T s is your expected project completion time, and sigma e is the standard deviation of the schedule time, what is the schedule. So, I may say that what is the probability that the 90% chance that the project will be completed, then what will be the value of T s. So, from using the cumulative normal distribution table, we are having the cumulative normal distribution table. From that table, we can find out the corresponding value of the standard normal value we can find out. Then, what is the probability of completion of project is schedule time is we can calculate from there itself. So, these are the three things. Now, we will try to find out some examples. Using examples, we will try to complete, try to explain the methods. First, see the problem. A small project is consisting of 7 activities, the details of which are given here. You see the headings. In the headings, we have told that the activity, what is the duration. Now, duration you are using not a single time like CPM. Here we have supplied most likely time, optimistic time and the pessimistic time for a project, and what is the immediate predecessor. For this example, I will draw the network using this one. Your starting point, we are telling that you are starting from here. So, you are having this, your starting point, this is the activity A. If you see the table, B precedes A, we have told B is preceding A. So, your B precedes A, we are drawing this. After that, we are having this one, that the For C, it precedes, immediate predecessor is C. So, you can write down, draw this. So, your immediate predecessor is C. Next you see D, the project completion time is D, and for D, what are the predecessor? Immediate predecessors are B and C. So, I have to use, if it is D, say immediate predecessor is this one D, but we have told immediate predecessor is both B and C for D. You see, for D, immediate predecessors are both B and C. So, here you have to now draw one dummy activity, say D 1. You have to draw one dummy activity D 1 over here, because before D completed, before D starts, both B and C should be completed. For that one, we are using this dummy activity D 1. The next one E, immediate predecessor is B, that is from B here E can come. So, we are writing E over here, after B the activity E is there. Then F, activity F, we are telling it immediate predecessors are D and E both, that is if I draw something here and if I draw, say this is the activity F, of course, F before F E should be completed, but D also should be completed. Since D also should be completed, therefore, we have to provide one dummy activity D 2 over here, one dummy activity D 2 over here, and the last one is, if you see, the last one is the activity G, immediate predecessor is D. So, this is D. So, immediate predecessor is D and this is your G. So, this is the first thing we have drawn the network diagram. Now, then we have to find out what T E and sigma square. What is your T E? From the formula, T E is T 0 plus 4 T m plus T p divided by 6. This is one. T E is T 0 plus 4 T m plus T p by 6, and your sigma square is 1 by sigma square is 1 by 6 into T p minus T naught, T p minus T naught, this whole square. So, these are the formulas sigma square and T e. Using these formulas, and if you see the table, in the table you have been given T p, T o and T m, T o and T p is given. So, now we can form a table like this way. We have the activity, we have this activity. For this activity, then we have to calculate T 0, T p and your T m. Once I know T 0, T p and T m, using the formulas T e and sigma square, I can calculate. So, you see the first activity. For the first activity, what is T naught, T p and T m? Just let us see the table once. On the table, it is T o is 1. If you see T o is 1, so I am writing T o is 1. Your T p, if you see in the table, your T p, that is the pessimistic time, is 7 and T m is 3. So, T p is 7 and T m is 3. On the same way, from the table you can write down the activities for the others also. I am not going to the table. For B, it will be, if you see for B, one see the B, for B T o is 2, T p is 14 and T m is 6. So, we are writing for B 2, 14 and 6. On the same way, for C, it will be all three are same, that is 3, 3, 3. For D, it will be 4, 22 and 10. For E, it will be your 3, 15 and 7, this 3, 3, 15 and 7. For F, it will be 2, 14 and 5. For G, it will be 4, 4 and 4. So, once you have calculated, you have written this table, now you can calculate T e. T e is T 0 plus 4 T m plus T p by 6. So, you can calculate it. I am just writing directly 3.33, 6.66, then it is 3, 11, 7.66, 6 and 4. On the same way, sigma square you can calculate 1 by 6 into T p minus T naught whole square. So, this will become 140,944 and 0. So, basically now we have to calculate the, once I have calculated this T e and sigma square, from this T e now I will calculate the earliest completion time and the least completion time using the forward and the backward pass formula. The forward and backward pass formula, that is using T e and T L, whatever we have done for CM. So, please note that you are having 3 times, that is T p, T o and T m. Using these times, that is the most likely time, optimistic time and the pessimistic time, you are calculating what is the expected time T e and what are the standard deviation. Now, we can proceed to the next one, that is how to calculate this. Now, using this table and the next one, I am just first I am drawing this one again, so that it will be, or just I am drawing it, it will be easier for you. Now, I am giving the numbering it 1, 2, 3, it is 4, D is here. So, 5 will come over here, 6 is here, your 7 will come, you are joining this, the arrows will be in this direction, there will be one dummy activity from 3 to 4 and there is another dummy activity that is from 5 to 6, therefore, this is your D 2. Now, for 1 to 2, basically it is the activity A. For the activity A, now what is the expected time then? Expected time you are calculated from this table. Please note now the difference. For the time activity A, expected time is 3.33, for the activity B, expected time is 6.66, like that. So, for the activity A, now I am writing 3.33 here. For the activity B, it is now 6.66. Similarly, if you see the table for the activity C, it is 3, for the activity D, it is 11. So, for the activity C, you are calculating it is 3, for the activity D, it is 11. Then, for activity E, it is 4, for activity F, it is 4. So, for activity F, it is 4, right, and it is this one. So, therefore, your time taken will be for activity E, it is 7.66, for activity F, F is on this side, for activity F, it is 6, activity E 7.66, activity F is 6 and activity G, it is 4. So, this is your activity G, for this the expected time is 4. For this D 1 and D 2, they are dummy activity, therefore, the time taken should be considered as 0. So, once I got this expected time, now I can calculate using forward pass and backward pass your values of E and EI and LI. So, E 1 is your 0. So, your E 2, this one, your E 2, this will be equals to 3.33 only. Your E 3 will be 3.33, 6.66. So, E 3 is your 9.99. Similarly, your E 4, this will become how much? E 4, you see in this side, if you go 1, 2, 2, 4, it is 3.33. On this side, if you go 9.99, maximum of these two, since you are using forward pass, so it will be 9.99. Basically, we have discussed these things in the last class when we are solving the problems. So, I am not wasting time on that. I am directly going to E 5. E 5 will be 20.99. Your E 6, this will be becomes E 6 will become also 20.99, because 6 is coming on both sides, 9 plus 7 16, here it is 20, and this one will be E 7 will be 24 point, sorry, E 7 will be 24 and here it is 6. So, 26 maximum 26.99. So, your L7 is 26.99. Your L6 if you calculate, your L6 will become 20.99. Your L5 this will be 20.99. Your L4 will be 9.99. Your L3 this will be 9.99. L3 is also 9.99. Your L2 this will be 3.33 and your L1 is 0. So, L1 is 0, E2 are same. So, now find the critical path. You see at every point the values are same. So, there will be more than critical path, critical points will be your A, B, that is what would be the critical activities? Your critical activities will be A, then B also will be coming. After that your C is not coming, your B will come, that is this one D1 I am not writing. After D1 your D will come. So, this D will come. After D it is again this is not critical because 26 minus 4 is 22, it is not matching. On this side it is matching 5 to 6 will not be there, D2 6 to 7. So, A, B, D and F. So, basically if you see the critical path will be 1 to 2, 2 to 3, then there will be one path that is 3 to 4, there will be 4 to 5, then 5 to 6 and after that 6 to 7. So, your critical path is, if I am to write, then 1, 2, 3, 4, 5, 6 and 7. And the project completion time is 26.99. So, this thing using expected time, first you are calculating from the most likely time, optimistic time and pessimistic time. What is the most expected time? Using the expected time, using the CPM methods, the forward pass and backward pass, you are calculating the EI and LJs, earliest completion time, latest completion time, and after that you are finding out the critical activities and you are finding the critical path. So, this is the first part of this one. So, what is the variance of critical path now? The variance of critical path, if I have to see the variance of critical path from this table, that is what are the critical activities? Critical activities were A, B, D and F. So, therefore, 1 plus 4 plus 9 plus 4, this should be the variance 1 plus 4 plus 9 plus 4, that is 10 plus 18. Variance we are getting this one, and expected completion time is, this is the from the variance already we calculated. From there, for the critical activities you found the sigma square, adding up you are getting the variance of critical path. So, you can say that your TE is 26.99, that is the expected completion time of the project, and your sigma square, this is equals, or sigma square is 18. So, your sigma you can write down your root 18. Now, if you see in the problem, just see in the problem, let us see the problem. The first part we have done, draw the network, find the critical path and expected project completion time. The expected project completion time is your 26.99. Now, see the number 2. Number 2 we are saying what project duration will have 90% confidence of completion. That is, if I am 95% confident that the project will be completed in what time. So, let us see the calculation now. We know the probability of Z less than equals T s minus T e by sigma e, this is equals then 0.95. Now, if you see the normal table of the normal table, if you see, then the Z of 0.95, you will see that the value is becoming 1.64. Therefore, what is happening? Your T s minus T e by sigma, this is equals 1.64. So, now you know what is T e, you know what is sigma, therefore, you can calculate what is your T s. If you calculate T s will be sigma into 1.64 plus T e, and T e and sigma already we have calculated. Therefore, your T s will become 33.94. So, I have 95% confidence that the project will be completed in 33.94 days, although the expected project completion time is 26.99 days only. So, I think from the problem it is quite clear that how we are proceeding to this one. So, let us take the second problem, not this, first let me see this one, that is the cost slope is there, following table. We are telling that the following table gives the activities in a construction project and the other relevant informations are also there. Here we have given, you see, what is the time for completion, normal time for completion of one activity, what is the time for crash time, that is if I give extra benefit, extra incentive, then what should be the time. So, now I am putting the data in two different way. One is I am giving what is the normal time, what is the normal crash time. Similarly, I have given what is the normal cost and what is the crash cost, that also I have given over here. This I am telling as direct cost, and there is another cost which we are telling as indirect cost, that is if the project is completed in 15 days, indirect cost is 600. If it is completed in 14 days, indirect cost is 500. So, depending upon in how many days the project will be completing, what would be the project duration, what is the indirect cost, that you can calculate from this table. So, we want to draw the arrow diagram for this project and we want to determine the cost. So, this is your table. I am not wasting my time this, I am directly first I will calculate what is the costs and other things. So, I am drawing the from this, if you see from this table I am drawing the network first. I am not explaining because already we know how to do it, from the problem itself it is given clearly. You are having this A, you are having this 4, say we are denoting it as B, this is your project B, and this is your C, project C, activity C is there. From there one arrow will go over here, there is a one activity 5, the activity 5 will come from 2 to 5, this is F, and there will be another activity from 4 to this is G. Now, just let us see the table. From the table we have seen that what is the normal time, what is the crash time. For A it is 4:3, for B it is 6:4. So, what I am doing for A, I am just in the side I am writing 4 and 3. So, the first number denotes what is the normal time to complete the activity, this activity A. For B similarly it is 6 and 4. For others I am directly writing, you can see for C it will be normal time 2, crash time 1, and then for F it is 7 and 5, whereas for G it is 4 and 2. So, using these normal times, now I can calculate what is the earliest completion time, what is the latest completion time. So, again your E 1 is 0, so your E 2 this is will be equals to 4, your E 3 this is equals 2, then your E 4 is coming from 2 cases, this is 6, this is 4, this is sorry 2 to 4 there will be another arrow, 2 to 4 there will be another arrow, that is D, time is 5 and 3. 2 to 4 that is, just see, let us see this one, D is coming, immediate predecessor is A and it is 5 and 3. So, this I forgot. So, D 5 and 3. So, here it is 4, 5, 9, 9 is the highest one. So, E 4 we got, then E 5 will be 9 plus 4 13, here it is 12. So, 13 is the maximum. So, now come to the backward one, L 5 is this, L 4 will be equals to nothing but 9. So, your L3 will be for 3 4 it is 2 2 basically, for 3 4 it is 2 2. So, 9 minus 3 it is 7. For L2 it will become 4 and for L1 it will become 0. So, if you see the path, your it will be from 1 to 2, it will be from 2 to 4 and it will be from 4 to 5. So, basically the critical path is 1, 2, 4 and 5, that is A, D involves A to D, D to G, A to D, D to G. And what is the duration? Your duration is equals to, duration is 13 days. Duration is 13 days. What is the cost now? Total cost. Total cost, as I was telling you, it will be indirect cost plus direct cost. Indirect cost plus direct cost. If you see the second table, if you see the second table, I am completing the project in 13 days. In 13 days, indirect cost is 400. So, therefore, I will write it this equals 400 plus the summation of costs at the different nodes. And this summation of cost means, if you go to the table, that is 60 plus 150 normal cost I am talking about. So, 60 plus 150 plus 38 summation of that normal cost table, and if you calculate this value total. So, this is equals to 400 plus 60 plus 150 plus like this way dot dot it will go up to 100. This summation I will get 1113. So, once I got the cost as this one. Now, what is your cost slope? Your cost slope is equals to now cash cost C c minus normal cost by normal time minus crash time. So, your cost table slope now you can calculate for each activity, that is A, B, C, D, E, F and G. For each activity you can calculate this one. You see the crash cost minus normal cost by normal time minus crash time. Just let us see the table. Crash cost minus normal cost, that is 90 minus 60 divided by normal time minus crash time 4 minus 3. So, for activity A basically it is 90 minus 60 by your 4 minus 3. I am calculating for one, like this way you can calculate for all others. So, for A it is 30, it will be 50, for it will be 50, it is then it will be 22, 50, it is divided by 0, E for F it is 30 and for G it is this one. So, if you see the activity A has the lowest minimum slope. Activity A has the minimum slope over here. I am first talking about A, then I will go to the activity F. I am finding the minimum slope for this one. So, the activity A has the minimum slope over here. Activity A has the minimum slope means what? The normal time is 4, the crash time is 3. That means, you can reduce it by 1 day only. So, what I can do on this diagram? I can reduce the activity of A by 1 unit only, and I can make a new table from here. So, again I am drawing first, because 1, 2, 3 it is there, then 4 is there, 2 to 4, 1 to 4, 3 to 4 is there, then 5, 4 to 5 and we are having our 2 to 5. Your activity now from 4 it has now reduced to 3. Please note this one. Your A it was earlier it was 4, if you see it was 4, now we have cashed it by 1 unit and it has become 3. Like this way all others will remain same, that is B, C and your D, E, F. I am not writing for all others. If you calculate now on the same way, you will find that the critical path what you are obtaining is this one. One is this A to B, 1 to 2, then 2 to 4, this one is coming and then you are coming 4 to 5. So, basically now your path is 1, 2, 4 and 5, this path A, D and F. But since you have crashed it by 3 units, if you see, therefore, your L5 if you calculate, I am not calculating the others, it will be reduced by 1 unit. So, that it will be 12. In the earlier case, if you see, since it was 4, the critical path remains the same, but since you crashed the activity A by 1 unit. So, therefore, the total completion time has been reduced by 1 unit and it has become from 13 it has become 12. Again, if you calculate the cost, you will find indirect cost plus the normal cost. Indirect cost plus normal cost, your indirect cost for 12 weekdays is 250. So, basically now it will be 250 plus other terms will come over here. If you calculate it, then it will become 993. So, now if you want, you have reduced the cost from the earlier one, it was the earlier 1113, from there you have further, you have reduced this one, and if you go on, now if I further reduce another one, now what is happening between activity D and G, if you see this table, activity D and G, activity D and activity B, these two I can crash further and I can check what is happening. That means, your B is 64 and your between activity D and G, if you see, I am crashing the activity D by 2 days. Why activity D by 2 days? You see, activity D has here 5 and normal time 5, crash time 3. So, you can crash the activity D by 2 more days. If you do like this, that is, if you crash this activity D by further this, I am not drawing, this is 3. Earlier it was 5, now if you make it 3. In that case, your this time again will be further reduced to L 5 equals 10 and your E 5 equals 10. So, whenever your project completion time, total time is 10 days, then if you calculate the cost, your cost again will become 9, 4 and 3. Still your critical path remains same 1, 2, 4, 5. So, you see, like this way you are crashing your activities, that is, you are reducing the time of each activity, and by that way you are increasing the cost, but you can, it gives you the mandate that you can complete the project in time. After this, if you wish, again you can crash it, but if you crash, you will find, you can check of your own that the time taken is becoming or the cost is increasing and the duration is also increasing. So, we will stop here, our optimum result is this. So, the basic idea of PERT is, if you see the PERT, for PERT you are having the expected times, most likely time, that is CP, CO and CM. From these you are calculating the expected time, from the expected time you are calculating your critical path, from the critical path what is the actual cost you are finding, actual cost is direct cost plus indirect cost, and then you are finding the cost ratio. From the cost ratio, whenever I am finding out the cost ratio, whatever activity has the minimum crashing ratio, that particular activity can be crashed by the number of days as given in the data. Please note that non-critical activity cannot be crashed by that. You cannot shorten the duration, that is project completion time will not be shortened over there. So, like this way we can complete our project in the PERT. Thank you.